No, I'll make sure that you just,
It's fine. It's
you'll
fine.
finish this thing on time. Just time them. Yeah. So, you're live.
Right, so it's my my pleasure. What, need to put back my wedding ring.
What did you do before?
Well, I took it off, then I put paste, then I put it back on.
That's an important to your wife.
So it's my pleasure to introduce Yves Bertot. So we have the chance to have two people with female names on stage. We have Yves and Jasmine. So, or Eva, or
Yeah. Yves is okay.
Yves is okay. And yeah, so I'm going to talk about some building blocks towards modeling the physical world, some mathematical building blocks, and maybe some scaffolding, or no scaffolding in your talk?
Well, I don't know if I understand the meaning of scaffolding as it was used before.
Yeah, okay.
So, my talk will have three parts actually. The first one is about a general objective that I would like to tackle. But the technical part of the talk is not going to be so much related to this, because I think I'm in the very first steps of looking at this project. So there will be a general discussion about why I think it should be interesting to go and look at a certain class of problems. And then I will pick two kind of problems and show you what has been done recently in these. So one is, the first one will be work in progress, and the second one will be a piece of work that is almost finished. So first, what is the main objective that I would like to tackle? I'm not so much interested in big proofs just for the mathematical setting. I understand the restriction that somebody like Tim Gaworth may have about the fact that the tools we develop may not be a help for mathematicians. They will be a help for people who want to build complex designs with less mistakes in the designs. But when you want to really think about new patterns of abstraction, using a computer that is frozen on all patterns of abstraction may not be the right thing to do. So I will not push too much the idea that we are doing mathematics on the computers, but we are using, trying to develop complex designs in which mathematics play a role. And so we don't have to be at the forefront of the evolution of mathematics to do that. So my idea is that it should be interesting to look at robots, because as was explained in the first slide, but I didn't say it, they are becoming more and more used in our daily life. And so the fact that they are safe is a big issue. And one of the problems with designing robots is also that it's very costly to build the physical thing. So if you can start thinking about it in complete ways before having the physical thing, it's very interesting. I will come back here. I would like to say one thing that is, I think, quite important is that actually, if you look at the literature around Maple, you can already use computer algebra systems to do a lot of reasoning around robots. And it's not completely sure that theorem proving is really the first step that people would want to do. If you want to be able to reason in the computer about a design, it's already good to do a lot of symbolic computation without necessarily having a lot of proofs in there. So for me, this robot idea is more of a mine of problems, like a mine of problems. So I'm trying here to list a few of these problems. You might want to think about the mathematics that go in the mechanical design. So there's question of geometry, and there's question of what are the various characteristics of the mechanical parts. Then also there's questions of control, and we see actually currently that we are making a lot of progress in being able to reason about control issues in theorem provers. There are problems of sensing, visual perception of the world. This uses a lot of geometry, projective geometry and things like that, on which we can do things. Dead reckoning is not very important, but the fact that there may be a discrepancy between what you recognize with a camera and what you measure with looking at how your wheels go and things like that is something that has to be reconciled. And we have to it may be interesting to look at the mathematical problems of reconciling various sources of information about the world. And so you have uncertainties everywhere. You never know exactly whether you actuate as you requested. You never know whether your sensors are perfectly giving you good information. So there's already been research into improving about probabilities. I think this is a nice place where this could be used. I will spend a little more time on questions around motion planning, but there's already been work that's been done, especially at NASA by César about collision avoidance between moving objects. And so these are things for which we probably already have a lot of building blocks. There are other aspects where people are thinking more and more about autonomous subjects, and people are thinking about using more and more artificial intelligence. And I think on that side, well, we are pretty naked for now, so it would be interesting to see what you can say about it in our form of proofs.
Did you say what SLAM is?
SLAM is simultaneous localization and mapping. So it's when you discover the world as you are making the map, and at the same time you're moving in the world. I intended to tell what the acronym was. So these are just pictures about what the various aspects that can be looked at. So I will spend some time on the upper left corner, because this is one of my current projects, looking at Delaunay triangulations and how they could be used for motion planning. And then there's another project that's happening in our group in Sophia, which is about understanding control. So we start with general theorems in the theory of dynamical systems. So the illustration on top is taken from one of my students, a student that I supervised with Cyril Cohen, who is named Damien Roulin, and who has just formalized a basic theorem in the theory of dynamic systems that's called Lassalle's theorem. And so then we plan to use that probably to start with a sample scalar example, which is like the inverse pendulum. And this in turn could be used as knowing how to do that could then be used as a step towards robots that exist, that are involved in bipedal march, marching like walking like humans. So there are two aspects that are amenable for formal proof that I want to look at. There are much more in my introduction, but I will spend some time on questions of computational geometry. There are very few teams in the world that do work on computational geometry. I think Jacques and I know everybody that does that by that Christian name. But maybe we're wrong. And another aspect which is more related to recent work, and maybe not so related with robots, is about how you go from a mathematical proof to a computer implementation, and with a funny example, well, an example that I hope you will find funny. So one of my objectives over the last few years has been to look at the formalization of the Delaunay triangulations. We already published a paper in 2010 on the topic. I will explain why they are interesting. Well, actually, this drawing is a help to having the explanation. That when you have a set of points, like here the 6 yellow points, when you have a set of points like here, the 6 yellow points, you can build triangles that are based on these points. And if the triangles that you build have a nice property, which is called the regular property or the Delaunay property, then the lines that are drawn by connecting the centers of the circumcircles for these triangles are safest paths between the points. So if you consider the yellow points as obstacles, then the red roads that are actually obtained by connecting the centers of circumcircles are safest paths between these points. My drawing is not completely right, but because this, which one is it? This line here should be perpendicular to that one.
It's a line bisector.
Huh?
It's a segment bisector.
Yeah, so they are all same segment bisectors, so they are guaranteed to go as fast as possible between the, as far as possible between the obstacles. Okay, so this is a property that is described in some books on robotics as one of the key elements to be able to, that can be used for motion planning algorithms. So this is why I got interested in this. So what we are doing right now is that we are trying to have an abstract description of this idea by avoiding to mix at the same level of study the numerical problems and the logical problems. So we first try to understand what are the logical problems of having triangles that do not intersect each other and points in various triangles. So we start this study by looking at a proposal by Knuth in the early 90s for the computation of convex hulls. He has a notion that he calls counterclockwise systems, which are triangles where you turn left when you go from the first point to the second one to the third one. So the triangles have ABC is not the same as BAC, and you want to keep the information that you are turning in a certain direction. And this is a basic element, and then
It's all two-dimensional, right?
yes, this is all two-dimensional, and actually I would like to go to three-dimensional, but this notion here, I don't know yet how I'm going to generalize it. I think there is already some literature in that. So here, this drawing here is just to help you understand that once you have defined this notion of always turning in the same direction, you can describe quite precisely the notion of being inside a triangle or being inside the convex hull of a set of points and things like that. So when you define a triangulation, you basically define it as being a set of triangles that are based on a set of points that were given you as input, and you want to have all the vertices of the triangles to be the ones in the data, and you want to avoid that the triangles have intersections, like the inner part of the triangles have intersections. So you can describe this, and you want also a few things more than that. You don't want a point to be on the edge of another triangle, for example. So all these conditions we described formally, and then we looked at operations that transform a triangulation into another one. For example, by adding a point in an existing triangulation. So you need to find a triangle that will contain that point and then add new triangles inside this one. And if you want to look at the Delaunay triangulation, it is usually done by finding edges that are unsatisfactory and replacing the two triangles they connect by a new pair of triangles with a better property. And so then, we are currently working on this. We are in work in progress stage. So we are only doing this, and we assume we are working with finite data. So we don't look at optimized ways of finding the right triangle, something like that. But these are steps that we are going to study later, finding triangles, finding the edges that needs to be flipped when you do Delaunay, when you want to obtain a Delaunay triangulation from a non-Delaunay one. So one of the question of taking an arbitrary triangulation and making it a Delaunay triangulation was already studied in a paper by Dufour and myself in 2010, which was presented in Edinburgh. And it had a nice question about proving determination, which comes down to using the fact that the data is finite. So what I would like to be able to do with this is go to higher dimensions and do the implementation as refinement of the formal proof. Right now I have C implementations of the algorithms, but they were completely redone by hand.
Why do you want higher dimensions?
Because if you want to think about an articulated robot, every time you have a point, you actually have a dimension. So I would like to go not only to 3 dimensions, but arbitrarily high. The problem is it may not be the algorithm that people in real life use, because high dimension Delaunay triangulation is a very costly algorithm. So then, in the first part, I explained to you that we reduce everything to just a logical property. Well, actually, we have 2 logical properties. The first one is whether a triangle turns in the right direction when you take the three enumerated points, or whether a point is inside a circumcircle of another triangle. And so these properties, what we try to do in our work is we try to collect all the logical, these predicates, we try to collect all the logical properties they have, and then reason only at this logical level. But at some point we have to go concrete and show how this is implemented in analytical geometry using the coordinates. And in fact, the counterclockwise idea is implemented using a determinant and then the logical properties. Well, at least for the convex hulls, the logical properties come directly from that. So we already proved that in 2001 with David Pichardy. And when we come to Delaunay triangulations, we have to mix this with the property of being inside the circumcircle. So just to give you a little information, this is how you compute whether the 3 points follow the same orientation as the plane, the coordinate system of the plane. You check that whether this determinant is positive. And if you want to know whether, if you already know that this minor determinant is positive, then if you want to know whether a point is inside the circumcircle of this point, whether the point x4, y4 is inside the circumcircle determined by these 3 points, you only have to compute this determinant, and I think it's negative if you're inside and positive if you're outside. Well, actually, it's negative if you're inside and this determinant, this minor determinant is positive. So then you want to connect the abstract level of reasoning with the numeric level of reasoning, and this is done by using a lot of properties of the determinant. And actually, for me, it's quite easy to reuse work that's already existing in the math component library about all the determinants. So we had a few problems about how to handle all the triangles. Basically, when we have 3 points, we would like to build a triangle from them, but we have side conditions, so that makes everything a little more complicated. If you have 3 points and they are two of them are equal, actually, what you obtain is not exactly a triangle. And how do you enter that with the rest? But what I would like to do in our work, so I can show this to people who will want to see more details, but is to have a very abstract level where I basically consider a triangle to be a set of points. And in the best case, this set of points has a cardinal tree. And then if we want to move towards efficient implementation of the algorithm, we may have to explore more efficient data structures. And my co-author in the paper of 2010, Dufour, advocated using hypermaps, which are actually the same kind of data structures that Georges used for the 4 colors here. But what I would like to avoid is to have the hypermaps play a role right from the start into formalization, because it makes everything more complicated. So I would really want to have the move from the abstract presentation to the efficient implementation to be viewed as refinement. Okay. So this was the first part. This is work in progress. I had an intern working on this this spring, and we can look at the code that's been written. It's available on GitHub, so we can talk about it for people who are interested later in the day. So
To clarify, do you form all possible triangles? Because that would be essentially cubic. The number of triangles of a finite set of points.
I know, I only form the triangles that I need for my algorithm. The set in which I work is the set of all possible triangles. It is essentially cubic. It's very interesting to know that it's finite, but I don't need to build it.
You don't need to somehow conceive it.
No, I don't need to have it anywhere represented in my memory. I only need to represent the triangles that I truly built at
For
any
a
time.
particular path that you already know that you want to follow or something like that.
For triangulation.
I only build the triangles that belong to the triangulation that I am considering, which is
Oh, I thought
whose
triangulation
complexity
emerged
is much
from the
lower than the
triangles.
set of all possible triangles.
I see.
One way to do it is to take 3 points and to add 1, and to add another 1, to add another 1. If you have an operation to add a point to triangulation.
Well,
That's a
it's
So
a
you
planar.
grow a triangulation.
It's a planar map, so the number of triangles is proportional to the number of vertices.
By the
Because of the order formula.
I'm not quite sure. You can have triangles that overlap.
No.
No, I don't
Allowed.
This is
Oh, they're not allowed.
They're not allowed right from the
I
start.
see.
I only build objects that are triangulations. So right from the start, I rule out the possibility of building triangles that overlap. And then when I have a triangulation, I make it regular by flipping edges, but that does not change the number of triangles. And when I want to reason about termination, I need to have in my mind the possibility of considering all possible triangles or all possible triangulations, but I'm only looking at one. Other questions? So now let's move to another topic, which is much more related to analysis. So my point with this, what time is it? Oh, it's here. Okay.
Excuse me, but before going to the other topic, can you give us a sense, I mean, maybe other people already know, but I don't, can you give us a sense of how much of this is already automated in your prover? Because I don't know.
I think there is, right now, what is already automated. Well, I have a full description of algorithms. I have several full descriptions of algorithms to compute convex files.
Okay.
And I have a full description of an algorithm that takes an arbitrary triangulation, an existing triangulation, and produces another one that is regular, that has the good property for the triangles. And the good property being that none of the data points is inside the circumcircle of one of the triangles. So let's go back to the drawing. Let's assume we remove this edge here and we put this one here. So in that case, this triangle would be in the circumcircle of these 3 points. So that edge would be illegal. By flipping it and replacing that edge with that one, I obtain 2 circumcircles that are much smaller, and in that case, this point is not part of the circumcircle of that triangle. So what you need to do is just find these edges that are illegal and flip them. And there is an easy computational argument to explain that this process cannot last forever. So this was already formalized, and what was done this year was to try to redo this formalization, but by avoiding using the complex data structure right from the start, which I found was obfuscating the problem. And in this new presentation, we haven't done everything. Where was it? We have described what it is to flip an edge in terms of the combinatorial of triangulation. And we have described what it is to add a point inside a triangle. But the other cases, adding a point when it happens to be on an edge, or adding a point when it is outside the convex form, have not been done yet. I know how to do it, but the intern didn't have time to work on it. So the intern is named Clément Sartori, and he's moving to questions of security now. So he won't work on that. So the next, so I have a half an hour for the second part. The next part is the end of a long-winded story that I had with the pi number. So I studied co-inductive types in year 2005, and I thought you could implement real number arithmetics just by using the co-inductive type of signed digits. Instead of just using digits, you have to use signed digits because otherwise you don't have very good computational properties. And at that moment, we wanted to show off a simple algorithm to compute pi, and we discovered that the Coq libraries at the moment had basically defined pi by giving an axiom about it. And that didn't seem right, so I spent some time cleaning up the library of Coq to make sure that pi is now a defined object instead of being axiomatized one. And so looked at various ways of computing pi, and I thought that it would be a nice way to conclude this investigation by looking at one of these algorithms that are used. Is there water?
Oh, and get some.
One of the algorithms that are used to obtain enormous numbers of decimals. Well, this is a very funny exercise, but it has no interest for my early objective of working on robots. If you are doing a robot, knowing 20 decimals of pi is probably enough. So I'm going to give you a crash course in arithmetic geometric means, which is one way of...
It's almost empty there.
Ah.
That's all that's left. I can go to the loop if you want.
So if you take two numbers and you compute the arithmetic mean, and you compute the geometric mean, the two means that you obtain are not the same But this one is always bigger than that one. And they're not the same, but they get closer actually. And if you repeat this process, it gets closer fast enough that as soon as the distance is less than 1, then after that, the number of common decimals that you know between the two numbers doubles at each step. So that makes, if you want 1 million common decimals between the two values, you only have to compute 20 elements of this sequence. So that's computing 20 square roots and other operations. Okay, so if you start with 1 and x, these functions an and bn are functions of x, and you can consider their derivatives. So you can also consider the ratio of an over bn, which should tend to 1 by being bigger. And if you consider Zn, which is the ratio of the derivative of b prime and a prime, then these two functions, yn and Zn, satisfy these recurrence properties. Now, let's go to computing p. If you start with, if the value you choose for x is 1 over square root of 2, then you can define this sequence by n. And you can also define this one. They are related in some ways. So this one uses the yns and zns, and this one uses only the a and b's. And this one converges.
Is this equal sign in the denominator's properties?
They should not be there. That's a huge mistake. There's nothing here. Okay. So this one converges quite fast, and this one almost as fast. The multiplicative factor here has a 2 to the power n in it. So it's still, the multiplicative factor still diverges, but its magnitude is negligible with respect to the inverse of the magnitude of this number. So that makes, if you want to compute 1 million decimals of pi, you need to compute only 20 elements. That's the same property as I said before. And for this one, 20 elements will be also enough. The 2 to the power 20 is only 1 million, and 1 to the power 20, yeah, it's only 1 million. And 1 million is 6 digits to compare with 1 million digits, so it's not important. Okay, so when you want to do the proofs about these series, you need to have a theorem prover, or if you want to do formal proofs about this, you need to have a theorem prover in which the notion of improper Riemannian integral is defined. So in my case, when I started the experiment 3 years ago, I had to define myself the improper Riemann integral. And then so I show here two integrals, this one and this one, because this one is a proper Riemann integral, and you need to be able to move from this one to this one. So you need to have a lot of variable change properties and things like that. In particular, the variable change capability is needed to prove that this value is the same if you replace a, b by one step of the arithmetic geometric mean process. And so if you write m for the common limit of the two a and b sequences, and then you have, this is a way to compute this integral. So these integrals are called elliptic integrals, and they were studied intensively in the beginning of the 19th century. And Gauss had found this property. It was found in his footnotes. So a lot of people claim that Gauss knew how to compute pi with this, but if I look in the Voronoi book about this AGM process, it doesn't say so. It only says that Gauss knew that if you knew pi, then it was a nice way to compute elliptic integrals very fast. So what I want to be able to do is do the proof at the real number level, so that where you will have questions of integrals. Then I want to be able to talk about the rounding errors that are going to happen during an implementation. And I would like to have the exact implementation available. So at the mathematical level, just to connect to other talks that we heard during our stay here, it's true that this is just undergraduate mathematics. So there's nothing to write home about in terms of discoveries. What you need is to have the possibility to talk about improper Riemann integrals and Riemann integrals. You also need to be able to have theorems about uniform convergence of functions, their continuity, and the properties of their derivatives. I look at Riemann integrals, but I don't compute them. They are only used as a way to do all the mathematical steps of reasoning. In particular, at some point, we try to understand what is the equivalence. If we look at this derivative here, when x goes to 0, this function I of x behaves like the logarithm of x. Well, maybe not the logarithm, the formula in which the logarithm happens. So what is interesting is, so there is no use of numerical integration as was described in the talk by Asia, but there is a lot of need for automatic proofs where we need to be able to compute derivatives quickly. We need to manipulate a lot of algebraic formulas in which we have square roots. So it's a bit too bad if you have an automatic tool that only works on the fixed set of basic operations on real numbers. And because there's a lot of square roots and squares and things like that, you need to be able to work beyond the capabilities of linear arithmetic. So if you want to see what I mean about this, I invite you to come and discuss with me. And for me, what is really important, my proof may be a bit long, because it's still a lot of details to get right, and sometimes it's too hard to say the thing in a simple way. But I'm really benefiting from existing libraries. This is where, at some point, the power of the proof system lies as much in the extent of its libraries as in the power of the language itself. So then I go to evaluating the errors. What I do is I take the same algorithm that was described in the first phase, and I replace most of the operations by operations for which I just assume that they introduce errors. And I have a bound on the error that is introduced by each operation. So what I used is directed rounding, which corresponds to what you would do if you were always I'm only computing positive values, so I'm always rounding towards 0. And what I discovered during these studies of computation is that even though, you remember yn was defined with a quotient and a square root, but what happens is that even though there are two operations that introduce errors, then as you compute more values of yn, you are never further away than 3 basic errors. That is, the basic error being the one that is introduced by either a division or the square root. You never have more than that, because the derivative of the yn of the scheme that computes the yn function is so low that the errors that come from previous computation, they get crunched down as you progress in your computation. So you add a few errors, but the one that was there before is just almost removed at each term. So in a way, you could say that if you look at the way YN computes, well, the errors that are done by the square root and the errors that are done by the division, they compensate. But they do more than compensating.
So do you get a theorem that says something like the absolute value of pi minus a number with a million digits is less than 10 to the minus, you know, 1,000,001 or something? So do you actually have to get the
Yes.
theorem?
I have a theorem which is not expressed in this. This was what I wrote here. In my theorem, I put I know that this is positive, and I know the constraint that's hidden in the big notation.
And it's a reflected computation?
No, that theorem is an abstract level computation. It's all done with real numbers on which you cannot do anything.
But you get the actual digits. How do you compute the actual digits?
Oh, but that's the later part of my talk.
Ah,
So once I have this one, which only talks about real numbers, the real numbers, they are symbolic objects in our computation. So basically, in the view of computation in the Coq system, which is different from what you have in Hall. In Hall, you only have symbolic computation. So you try to make it as fast as possible with efficient simplifiers and rewrite tools. In Coq, we have another level of computation below the symbolic computation, which is the one that comes with inductive types. So if I look at a real number and I know it is in an inductive type, it comes with its own computation rules, and these ones I'm going to leverage to do the computation inside Coq. But at some point, I need to establish a correspondence between the natural numbers, the efficient implementation of natural numbers that I'm going to be using, and the real numbers which are symbolic. So this is a step that somehow you would not consider in your usual framework in the method.
So just to clarify that again, what's your representation of the 1 over square root of 2?
Here,
The B0, how do you represent it?
so it is, one is an axiomatized value in the set of real numbers. And square root is an axiomatized function. It's an uninterpreted function with an extra property that says that it computes the square root. And so
none of these are actually numeric computations.
No.
All symbolic.
everything here is purely mathematical abstract thinking. And then, at some point, I say I will draw a parallel between this and a computation on true computer science, computer or technology objects, which are abstract data types or inductive data types, for which I know how to describe exactly computation.
So the real numbers are totally axiomatic at this point.
Yeah. In some sense, all the mathematics I've presented in this slide, they are all dependent on a bunch of axioms. They are consequences of a bunch of axioms. The fact that they are consequences is verified by the Coq system, but the fact that the bunch of axioms I'm using is relevant or correct or consistent, this is not part of the proof. This is something on which I rely. This is part of my truth. What I trust. Okay? So when I do the evaluation of errors, I still remain at the level of abstract real numbers. In this language of abstract real numbers, I can talk about very little values that would be inverses of real numbers that look like integers, but they are all real numbers. And at some point, I will just, I won't show you any code, but I just replace, I establish an isomorphic correspondence between the real numbers I described and integers. So what I do to do that is to say, now I will take integers, and all of them will be interpreted as that integer divided by a big magnifier. So in my case, if I want to compute 1 million digits of pi, I will take integers that are all supposed to represent the real number, which is that integer divided by 10 to the power 6. And so I do all this computation with these numbers, and what I obtain is the integer that is written with 1 million digits, because it's on the order of 10 to the power 10 to the power 6. For this data type, what I'm using is a formal an algorithm to compute square roots efficiently that was described in a paper that we published in 2003, and that was implemented on the data structure of Big Z by Voronoi and his colleagues. So I have a systematic correspondence between real numbers, that were the object of my first proof, and the natural numbers. I did all the proofs of the error analysis using real numbers, and only at the last moment I say these real numbers and these operations with rounding errors, they are refined by the operations on natural numbers. So I can do all these computations in COP with this data type, and there are various ways of doing the computations, and these various ways use different amount of trust among things that you do. And the first level of paranoia is when you only want to use the reduction system that is already provided in the system. At that level of paranoia, I don't think I can compute more than 1,000 digits. And then I can move to the second level of trust, which uses a virtual machine, a bytecode virtual machine inside the clock system. And with that level of trust, I can compute 1 million digits in 6 hours. And I can then go even one step further, and instead of using a bytecode virtual machine, I can compile the code into OCaml and then reload this code inside of Coq. So that means that I'm expanding the Coq system with a piece of code that was compiled from my formal verification. And if I do that, I have a computation that is of the order of an hour. And the second algorithm, the one that used a single division with a sum in the denominator, is even faster, but I don't have, I didn't redo the computations.
So, and that this is exponential. If you wanted 2 million digits, it would take just a fixed unit of extra time? Or are you have overheads of managing the millions of digits, though? How much would it, how long would it take?
I have to
2
study
million
this,
digits?
but I think the overhead, the overhead comes with every operation.
Yes.
Before you had an addition that took 10 seconds. If you do 2 million, then the addition may take 20 seconds. So every operation has an overhead. And then if you only add the overheads of the operations, that's still not enough, because the amount of memory you're managing is also bigger. And so you have the cost in memory management.
Mathematically, with the number of digits.
Well,
But
this
if you
would be
have
computing
twice as many
outside
digits,
Coq.
it will take 4,000.
But it wouldn't.
No,
You're extracting it from Coq and running
No.
it in OCaml.
no. I'm compiling, obtaining a piece of OCaml code, which is then in
But it's not computing
Including-
with Coq data structures, it's presumably computing with machine integers at that point, isn't it?
it's computed with a mix of Coq data structures and machine integers. That is, the leaves are machine integers, but I don't use arrays. So the bit data is represented as a bit tree of a bit binary tree of height 20. So of the order of 20. So that makes that every operation you do on this tree representation of big numbers is more of the logarithm cost than the constant cost that you would expect for.
So we'll have to wait for 2 million digits, it seems.
Yeah, I could do the computation, but you will
Probably,
have to-
I don't think you get a log of, you're traversing the entire tree, so that's linear time.
For an addition, yes.
Well,
But I was talking
I
about
think
just accessing.
You're not always accessing random.
No.
digits.
In fact,
You're doing it
I'm almost
sequentially,
never
say,
accessing random digits in the number. I'm always doing a full traversal of the tree, so that may be less costly.
You try, since you have this sort of contraction going on, you try doing the first computations with lower precision, first iterations with lower precisions.
Well, it happens only in one of the sequences. For the others, the errors accumulate much more. So it was not worth the effort of trying to come up with a scheme to do it, because it could only pay off once. So I'm finished.
Oh, let's thank the speaker.
No, I wanted to say something about the last few slides. I'm finished about the technical part. So the work on Delaunay, as I said, I wanted to mention that there was Jean-François Dufour who had worked on it before, and that it is related to Georges' data structure, the one that he uses for the four-color theorem. But the two pieces of development are really disjoint, because Jean-François Dufour never wanted to look at a new way of approaching the Coq formalization, in spite of my pushing it. The fact that the way improper integrals are implemented now, not the ones that I did in the beginning of my experience, uses filters, and so this is very much related to the work of Johannes, Fabian, and Brian in Isabelle. Well, actually, I think Johannes, Fabian, and Brian proposed the idea first as an element of theorem proving, and it was reused in Coq. The work I did on computing the large number of decimals for pi is also related to another algorithm that is funny about the pi number, one that makes it possible to compute only one digit without computing the one that precedes it. And this was already been formalized too by Laurence Rideau and Laurent Théry, who are members of my team. And so we published a paper together about it. And in fact, when we discussed with John Harrison, he told us that he had done it in the past. And if you look on GitHub, there's a file dated 2010 about it. Other people who try to do fast computation for pi, for example, inside Coq, there was Robert Krebers in Nijmegen. He uses a machine-like formula, but it doesn't go beyond 1,000 digits.
What do you mean by this machine-like formula?
So Machen is the name of a Scottish mathematician. So if you know French, you have a tendency to believe that it is Bull or stuff or whatever, but this is the name of a mathematician. So John Machen is the first guy to compute 1,000 decimal of pi. He used a formula based on arctangents of inverse of integers.
But Robert also does it like over the Nijmegen constructive rails, or doesn't he?
I have a hard time understanding what Robert does. I was not able to find the development, but I think the formalization is the proofs are connected to the CCORM library,
Yeah.
but the implementation is a very clever computer science implementation. And he knows he wants to work at a given precision, and he goes to the best precision he can do, the best data structures he can use for this precision.
I was getting the impression that what he did was much slower than what you described.
Oh yeah, it's much slower, but anyway, if you use this kind of formula, every new digit has a constant cost, so you cannot go very far. So I would like to thank all these people. Of course, the code infrastructure is important, and we should never forget about all the manpower that's been put in making such a system available, especially in this case, for the pi example, all the capabilities for computations have been done with a lot of work. But for me, it's really important, and I'm really happy to have this aspect that we start to be able to use a lot of work that has been packaged into libraries by people. So for me and Laurent, the mathematical components have been useful. So it's what is used for the first development on geometry. And in particular, there is a new extension to this library of finite maps and sets on arbitrary data types by Cyril Cohen that is being used intensively. And for the mathematical analysis part, the name of the library is Coplico, which means poppy, the red flower. And for part of my proofs, automation relied much on interval tactic by Lepion, and I forgot to cite Frédéric Besson for the linear arithmetic fragment. And I think that's everything. So if you want demos, I will compute 10,000 decimals in my office this afternoon. If you want, it will take only 5 or 10 seconds. Going further was a bit
No. Google tells me that 2.7 trillion digits are known.
Yeah, but
I know
my computation is bordering on at the level of symbolic computation.
Of course, I understand.
But you should read the paper about the Japanese guy that explained how he built the system to get this record, and it's very impressive how he managed to check. There is no hardware error, and so it's really
this is why the Borwein-Bailey proof formula is interesting, because people do statistical checks. Before that, they were not able to do that. They had to compute twice with different algorithms and check that they were the same. But now you can compute only once and then do statistical sampling to check whether the digits that you have are right or not. And you have the statistical proof. You wanted to?
Yeah, I was just going to make a comment. We have some libraries of Delaunay triangulations and Delaunay cells in whole light that we used for flyspeed. I don't know if there's overlap with what you want to do in 3D, but some of our work is in n-dimensional space and some of it's in 3 dimensions.
Is that in the whole white library?
It's in the whole lot.
No,
In
part of the
flyspeed project.
polytope thing. Ah, no, it's in the flyspeed.
Okay. So did it receive a separate presentation, or is?
Well, it's part of the big project.
It's part of the big project. Well, just of course, I'm going to look at this in the source and find it, but it would have been nice if there was an extra explanation on the side.
Yeah, the part on polytopes has been separated out by John Harrison.
Okay.
I had another question. I was wondering, is there any application of having a large number of digits for pi?
I don't think, I don't think there is.
It's funny enough.
Just going towards transcendence. So I have
Transcendence we also proved, but this is, that has nothing to do with computation.
Yes, yes, yes. But another outsider kind of question, but how does all this development of libraries and mathematical components that one needs to approach these big proofs, how does it impact the basic infrastructure of the prover? So is it constructed in such a way that it has no impact at all, or else it stresses it in some way?
It stresses it in some ways because if you want to be able, so this is the part of the scaffolding that George was describing. If you want to be able to share notations between a wide variety of data types that have the same structure, you need to be able to describe the data type and then connect it to the structure. And this requires some capability of either handling the unification or being able to recognize that somebody is in a given class. These are called type classes or canonical structures. And in our case, in the mathematical components, we discovered that even though the idea of type classes has been widely advocated, when you start to have a big enough library, you have to be very, very precise about what is happening in this kind of inference, whether you are satisfying a given set of axioms. And this is really a stress on the system. I think that was a point where, you know, well, I think George might want to add something about this, but there was an idea of canonical structures that was invented in Koch in the 1998, and it fell in dereliction. And then when George wanted to organize his development for the four-color theorem, he found that, decided to use it, but it had fallen in such dereliction that there were actually designs in the Koch system that prevented from using it efficiently. So it's really true that defining a library with reuse will rely on certain properties, and in that sense it is a stress on the development of the system. Maybe you want to add something? Or?
Because if you have multiple structures, then you start stressing the core type checker, basically the routines that actually compare types for equality. They have you can end up in corners where these routines behave exponentially, and you have to take some countermeasures to try to prevent this from happening, because if it ever happens, then the sky falls.
Yeah, one example of where you can have non-determinacy is when you compare two objects that have been defined, they may be hidden under new definitions, that is, new names have been given. And you have to choose whether you want to unfold the definition or not. And you have to do that on both sides. And the way you do it on both sides or not, or whether going deep first in one side or on the other, can have a drastic cost in the way the system recognizes that two objects are equal.
Yeah, well, I guess what's the trap is that there's a conflict between this expansion, computation, and comparison. If you want to compare things, you would like to do as little expansion as possible, because then you can figure out things are equal by looking at the short form rather than the expanded one. If you want to compute, you want to expand as much as possible, and the more you expand, the sooner you expand, the better. And as things stand now, the Koch system doesn't handle this conflict very gracefully. It tends to err on the side of expanding, which means it can get into trouble because it's expanded too much, and especially it does call by need So it can get into side-effecting situations where it needs to expand the definition to do one part of a comparison, and then that expansion gets shared by a side effect absolutely everywhere. So you get into situations where you can do two comparisons independently, and they both run really, really fast. And if you try to do both at once, then one causes expansion, and then the other one takes forever. Like literally forever.
If I may add another comment on that topic, one thing that I found very interesting but also very frustrating is the notation facilities provided by the system. This is an extremely important thing when you're formalizing mathematics. You have to capture somehow the way mathematics are written, because it's not only folding symbols, it's really carrying a lot of meaning and a lot of inference of canonical properties that are propagated along some constructions, set constructions, for instance. And it's not very easy to come up with this kind of notational device. And from our experience, I think it's difficult to do that. And it's also difficult then to help users search for concepts through their notations. There's always a question of having nice notations and also well-behaved in the indexes or something.
So I'd like to see concrete examples when we talk about that. Fine. So that brings up a question about what to do with Friday morning. So we normally have tutorials on Friday morning, and I was wondering if there's something people would like to see. So, I mean, I have a request actually. I'd like to maybe have Tom Haynes go over the flight spec.
Actually, Thursday is my last day here.
Okay. Thursday we already are. I think Andy Pitts is going to have a combinatorial type theory thing on Thursday. Would you be willing to do it Thursday though? We could do it. What do we have tomorrow afternoon? Is there a social proof thing happening tomorrow afternoon? I'll check if there's a thing. Would tomorrow afternoon work for you, Tom?
I'll talk to you about it quickly. Probably soon, but I'll need to check that out.
But we still have room for tutorials on Friday morning then, if people want to volunteer something. Maybe George could do the Mount libraries.
Yeah, sure.
I have a question. So when we did the formalization of Delaunay triangulation in Isabel, we used CAD a lot to help us figure out some of the lemmas and counterexamples, especially. What did you use in terms of realizing some of your lemmas, what have degenerate conditions and stuff like that?
I was the counterexample finder. So.
Yeah.
So that means that a lot of time sometimes was lost because I was not available.
Yeah, because CAD helped us. In many cases, we just say that's not right, and at least we could then think about it and refine the slide condition. Yeah.
So you did this, but it's not anywhere public yet.
So that was done by my PhD student and I a while ago actually. So when it was so it's not it should be. It's in her thesis.
About putting it in the AFP.
Laura.
Laura Maker.
Yeah. Yeah.
Yeah.
Yeah.
I have to go, sorry.
Oh, yeah. Last question by Joseph then?
Yeah, like plugging into the previous discussion, I don't really see exactly how your complaint about this mathematical components and the canonical structures plugs in to what you described with the computation of pi, because to me it seems that the computation of pi is a very sort of small theory, small development, which you, even if you somehow plugged it to math components, you probably should be able to optimize the notational search to be reasonably fast, and all these like corner cases which George is talking about. Like, was that sort of a general remark which you
It was a general remark.
Okay.
That was mathematical components and some of its applications put a stress on the clock system. But the development on Pi here is not based on mathematical components.
Okay.
So in that case, I'm more using the complete development and the variety of mathematical structures that appear there is much lower. The one difficulty for me was mostly getting accustomed with the notion of it.
All right, let's thank Yves again.